This is Prashant. In the previous video, we discussed about the basics of signal flow graph. Okay, today let us take one simple example on the signal flow graph. So this is the question. The system is represented by signal flow graph. We know that the signal flow graph is a graphical representation of set of linear equations, whereas block diagram is a pictorial representation. So both are represented by a system. Okay, the question is mentioned here. The question is to find the overall transfer function of the system by using Mason's gain formula. Okay, so Mason has introduced this concept in 1964 to find the transfer function of any complex system. Okay, the first step in finding the transfer function is identify the number of forward paths. Number of forward path. So as you look at it to the signal flow graph, so how many ways are there from the input node R of S to the output node C of S without traversing the node more than once? Okay, so in this signal flow graph there are two forward paths. The one forward path is from the input node G1, G2, G3, G4 and finally to the output node C of S, and the second forward path is like this: G5, G6, G7, G8, and in that case the no node is traversed more than once. Suppose if I go like this: G5, G6 minus H3, again I am coming to this node, this is going to traverse more than once, so that will not be the forward path. Okay, so in this signal flow graph there are two forward paths, and the forward paths are represented by P1 and P2. So next step is find the forward path gain. The second step is find out the forward path gain. So as I said, there are two forward paths, so multiply all the gains in the forward path. So let us take first one, P1 equals to the multiplication of all the branch gains in that forward path. So we have G1, G2, G3, G4. So multiply all the forward path, G1, G2, G3, G4. That is the first way we can reach from input node to the output node. And the second way is from G5, G6, G7, G8. So hence multiply all the individual branch gains, G7, G8. Okay, so once forward path gain is completed, the next step is, the third step is identify the individual loops in the signal flow graph. Identify the individual loops. Okay, so look at the signal flow graph. Identify the closed circuits in the signal flow graph. First one, we have the loop L1. It starts from this node and it is going to end at the same node. This forms a loop. And the second loop is, the loop starts from this point, the node 2, and is going to end at the same node. So that forms a second loop. So similar to that loop, we have one more loop. It starts from the node 3 and is going to end at the same node, loop 3. And the fourth loop is, it starts from the node 4, it ends at the same node 4. See, apart from these four loops, there is no combination of such kind of loops. Okay, there are only 4 loops: L1, L2, L3, L4. So next step in the signal flow graph is, so find the loop gains. Okay, so L1, so just multiply their individual branch gains. We have for L1 it is minus G2 into H1, so multiplication of these two branch gains. And for L2 we have minus G3 into H2, and for L3 we have the loop gain, so minus G6 into H3, and for loop L4 the branch gains is minus G7 into H4. So these are the 4 loop gains in the signal flow graph. Okay, next step is identify, we'll erase this one, identify the pair of non-touching loops. As we have discussed in the previous section, the non-touching loops are those loops which will not share the common node. See, for this example, in this signal flow graph, loop L1, L2 will touch each other at the node 2. So this will not form a non-touching loop. Look at the second combination, L3 and L4. So these loops will share at node 4. Hence, these two will not be the non-touching loops. Suppose if I consider loop L1, L3 these two loops are separated, they won't share any common node, hence this combination act as a non-touching loop. So next step is fourth step, identify the pair of non-touching loops. Okay, so as I told, first combination of the non-touching loop is L1, L3, these two combinations. So the next combination of non-touching loop is L1, L4. Those two loops will not share a common node. Next combination is, can I combine these two, L2, L3? That is also one possible condition. They won't share any common node. Then last combination of the loop is L2, L4. So hence there are 4 combination of non-touching loops taken 2 at a time. Okay. So once you get the values of non-touching loops, the pair of non-touching loops, find their gain. So L1, L3 is one gain. So L1, L4, L2, L3, L2, L4. Just multiply their individual loop gains. The next step within this one, so there is one more possible combination we need to check. Is there any combination of 3 non-touching loops in this given signal flow graph? Means all the 3 loops should be separated. They won't share any common node. Suppose if you see L1, L2, L4, they will share the common node 2. That is not a possible condition. Suppose if I see the loops L1, L3, L4, we have the common node 4. That is not a combination. So as such, there is no combination of non-touching loops taken 3 at a time. So means non-touching loops taken 3 at a time is 0. 3 at a time is 0. So once you get the terminology of all the signal flow graph, number of forward paths, number of loops, number of loop gains, the pair of non-touching loops, then we can use the signal Mason's gain equation to find the overall transfer function of the system. And the Mason's gain equation is given by Mason's gain equation for the transfer function is given by C of S divided by R of S, Laplace transform of output of the system to the Laplace transform of the input system, is given by summation of I equals to 1 to n. So Pi into delta I divided by delta, where Pi is the number of ith forward path, delta is the determinant for ith forward path, and delta is complete determinant of the signal flow graph. And delta is given by delta equals to 1 minus summation of all the individual loop gains L1 plus L2 plus L3 plus L4 minus the summation of the pair of non-touching loops is L1 L3 plus L1 L4 plus L2 L3 plus L2 L4, and there is no combination of 3 non-touching loops in this given signal flow graph. It is 0 minus 0. So once you get the values of L1, L2, L3, L4 and the combination of L1, L3, L1, L4, L2, L3, L2, L4, so we can substitute those values and we'll come up with the determinant of the signal flow graph. Okay. So as there are 2 forward paths in the signal flow graph, the Mason's gain equation can be written as C of S divided by R of S equals to P1 delta 1 plus P2 delta 2 divided by delta, where P1 indicates the first forward path and P2 indicates the second forward path and delta indicates the complete determinant of the signal flow graph. As there are 2 forward paths, I equals to 2. The next question is, we know the value of P1, we know the value of P2, we know the value of complete determinant of the signal flow graph, but we don't know the value of delta 1 and delta 2. So next step is to find the value of delta 1 and delta 2. Let us find delta 1. So delta 1 can be calculated with the help of determinant of the signal flow graph. Remember, so the determinant of the signal flow graph is delta equals to summation of all the individual loop gains plus the summation of the pair of non-touching loop gains. Okay, so look at the delta 1. So we have first forward path P1 equals to G1, G2, G3, G4. Okay, so eliminate the loops that touches the first forward path. How many loops are touching the first forward path? Loop L1 is touching the first forward path and loop L2 is also touching the first forward path. So eliminate these two loops in the determinant and make L1, L2 0 in the determinant. So if L1, L2 is 0, then the determinant reduces to 1 minus L1, L3 plus L4 as L1, L2 are 0. L1 equals to 0, L2 equals to 0 because these two loops are touching the first forward path. So second condition is to find the value of delta 2. Look at the second forward path. The second forward path is combination of G5, G6, G7, G8. So eliminate the loops in the determinant that touches the second forward path. In the second forward path, the loops L3, L4 is touching. So hence eliminate these two loops in the determinant. So once you make L3, L4 equals to 0, the value of delta 2 is 1 minus L1 plus L2. Okay. So this is how by eliminating the loop gains in the determinant of the signal flow graph, we can find the respective delta 1 and delta 2. So in this case now we have the value of P1, we know the value of delta 1, we know the value of P2, delta 2 and complete determinant of the signal flow graph. Hence we can substitute all the values and we'll come up with the complete transfer function of this signal flow graph. Finally, the signal flow graph transfer function is C of s divided by R of s equals to P1 delta 1 plus P2 delta 2 divided by delta. Okay, we know the value of P1 delta 1, P2 delta 2 and complete determinant of the signal flow graph. Substitute all these values and calculate the value of transfer function using Mason's gain equation. Yes, this is going to complete. Thank you for watching my video.